continuation of Algebra 2, specifically the ideas of factorization on polynomials. This is a continuation with Jerry's lessons for Algebra 2. My name's Sai, and hope you guys are doing well. So without further ado, let's begin. So let's do a warm-up problem for today. Let's first do these warm-up problems. We're going to first do factor this expression, expand the other expression, and we're going to identify the specific polynomial is a polynomial. So let's see the first question. So let's do the first warm-up problem. Part number one, really, of how we're going to factor this number. So really, over here we have a leading coefficient, which is, hold on, give me one sec. So what we have over here specifically is the following. We have a constant, and we have a leading term, leading coefficient. We also have a degree of 2. That's the most degree term that we have over here. You can say this is like x to the 0, which is essentially equal to 1. But in this case specifically, let's just try to factor this number out. So this is how we're going to factor it out. So we start first by looking at the notice that we're seeing here that for this part, 36x squared, this is a perfect square. 6x times 6x, because 36 is a perfect square. The x times x is just x. And we're seeing here that that's going to give us 6x squared. Now, after that, we can also see here in the constant variable over here, the constant is negative 121. We can distribute the negative sign. We'll keep the negative side outside. In this case, we can take a look at the 121. That can be 11 squared, which is 121. And then afterwards, the negative times the positive would give you negative. So in this case, also, you have this symbol as well. So we can see here that negative times a positive giving you a negative, and we're seeing here that the other numbers are going to give you the same stuff. So we're seeing here this number, and we're also seeing these numbers as well. These are giving us our answers. So that's set and cool. That's kind of really how we would factor it. Now let's do a warm-up on terms of how to expand a certain equation. So again, a lot of this is really revolves around distributing the expression that has the least amount of terms. We factor that out, and then for the other one, you do the same. You just basically complete whatever you do with the. So basically, you distribute the expression that has the least amount of terms, and you multiply that each time with the least number of terms. Each term you multiply that as many times, however long the longer equation, the longer expression has it. So we can see here that in this case, we're seeing here that we're distributing the 7x over the 9 because that's the least amount. And we're seeing here that the negative 9 is being distributed, and we're also seeing here the 7x is also being distributed as well. And afterwards, we're seeing here that we also have like terms as well. After that, once we distribute everything, we have like terms. So the 42x and the 27x squared, that's like term that gives us negative 69x squared. And we're also seeing here the 14x and the 54x, that gives us the positive 68x. And we're seeing here that you can drop the 18 down and the 21x squared cubed down, and that's really what our answer is going to be in that case. Now, let's talk about specifically how to identify if something is a certain polynomial or not. In this case, is this a polynomial? In this case, this is going to be a no, because specifically, because you can't have like an expression on the bottom. Like, you can't have a variable in the denominator. You can have an expression, but in this case, with a variable in the denominator, it's not possible, because let's say if x is 2, really the number, the solution is undefined. Anything divided by 0 is going to be undefined, and in this case, that's kind of what we're seeing here. So that's the warm-ups for those specific problems. Now let's go over really in terms of lesson 2 now. Prime factorization and geometric series are going to be going over. So let's start with polynomial factorization, really what it is. So what is polynomial factorization? We're going to shift in gears towards that. So let's talk about factoring monomials first. How do we factor monomials? This is how we're going to start. We're going to start with monomials and binomials, trinomials. There's a lot of meals in a lot of things. So let's talk about how to factorize that. So first off, factoring a monomial really means to express it as a product of 2 or more monomials. So let's say we have 6x to the 7th power. Let's say we have that. We're going to factor this out. So we have first, this is the coefficient of this expression, and we also have the exponent part. This is our variables part. So you can see here that we can distribute it like this. The x to the 7th, and remember, let's first talk about this part, the leading coefficient, or just the coefficient for this expression. We're seeing here 6 equals 2 times to the 3. 6 could be also 6 times 1. You can do it in both ways. In this case, either way works. So that's cool. And we're also seeing here x to the 7th. This is essentially similar to how to multiply exponents. We're adding essentially the small degree on the top. 6 times 1, 6, x to the 6 times x to the first. You're doing 6 plus 1. So you're doing 4 plus 3, 5 plus 2. That's kind of what we're seeing here in that case. And once we have that, we basically separate them. We're going to get, this is not the simplified one. The simplified one's over here. We're seeing here that the simplified one is in prime factorization 2 times 3. That's this part. This comes from here. And we also have the variables part for this, which comes from this part, however many combinations you have. So think about it like this simply, how to factor monomials. Monomials is one term. You separate it from the product of the coefficient and the number of variables in a certain given variable to an exponent. Anything with that, you can separate that to like the number of, you can multiply that however many times depending on the exponent, the number of variables. So that's kind of really what it is in that case. If that makes sense. Let's see an example problem. I think it might make sense afterwards. So let's say we have someone factoring this here, someone's factoring this here. So if you have factored 81y6 as 9 this, 9y to the third times 9y squared. Ahmed factored 81y to the 6 as 3y to the 6 times 27y. Which of them factored this correctly? So let's see here. Again, we're going to do the same thing as we did before. So we're seeing here 9y cubed times 9y squared. So let's just start with this part. 9 times 9, that's 81. That's good. Y to the third times y squared now. Y to the third times y squared. So notice we're doing y to the third. It's 3 plus 2 essentially because you're multiplying the exponent. This is actually y to the fifth, because 3 plus 2 is 5. So this wouldn't really work out. This one over here, we're doing 3 times 27, right? Hold on. I think if I color code this a bit better for you guys might be able to understand. Let's put this one, we're going to do 3 times 27 times y to the 6th times y. This is going to give me 81 times y to the 7th. So neither of these answers actually give us, our certain equation. This doesn't work, and neither does this as well. So really our answer is neither in that case. Our answer is going to be D in that case. Because we're seeing here y to the 6th, y to the first, it's just basically, there's an imaginary 1, y to the first is actually equal to y. So in this case, it's equal to y to the 7 in that case. So in this case, therefore, it's going to be neither in that case. You can see here that this is how we distribute it, and yeah, it's going to be neither in that case. Because once you do the distribution, they both are not going to give you that once you solve it in that distributed form. Now let's talk about greatest common factor of a monomial. So for integers, the GCF is the greatest integer that is a factor of both numbers. So for example, let's say we have the GCF of 12 and 18. 12 can be written as 2 times 2 times 3. 18 is 2 times 3 times 3. So hence therefore, we're seeing that there's two similar numbers, 2 and 3. You can multiply those, the GCF is going to be 6. So let's do 10cd squared and 25c cubed d squared. We can have here, for example, in this case, 2 times 5 times c times d. We're breaking it apart completely. And let's say we're trying to find the GCF between 10cd squared and 25c cubed d squared. Yeah, sorry about that, guys. So now let's talk about in terms of trying to find the GCF between 10cd squared and 25c cubed d squared. So we can just first break it apart completely into its complete broken form. So we have here 10cd squared is 2 times 5 times c times d. We also have 25c cubed d squared. That's 5 times 5 times c times c times c times d, depending on how many of the variable numbers there are, depending on the exponent. So we can see here that 5 and 5 is the same here. So we're seeing here 5, then 5 are the same. So really 5 is going to be one of them. And the GCF, we can see here that C is how many C's, the amount of C's has to match up. That's our max. So we're seeing here there's only 1 C versus 3 C's. Therefore, C is going to be, there's only 1 C that's going to make sense in that case. And we have 2 D's. So we'll just do D squared which represents these numbers. So yeah, that's kind of really what we're seeing here. The GCF would be 5CD squared. Let's try finding this GCF of the coefficients and the variables for these equations. Let's see, so we're doing this with multiple variables in this case this time. So for this one, let's find the GCF of the terms, the coefficients first. The GCF in 8 and 12 is 4 if you do the math. And also, x squared y and xy squared. So we can just break this apart, x times y times y for xy squared. And this is for x squared y. So we can just compare, we have x times y, really, that's the GCF for that. So x times y is going to be for this part, is just going to be x times y. So we're seeing that from here. And we're seeing that the 4 is being distributed from the 8 and 12. That's kind of where these numbers are coming up. So that's where, it's kind of where these guys are actually coming in. And we're seeing here that the x and y, they could just be distributed out because, that's kind of what we're seeing here. So the leftover terms, the x and the y, this is kind of the leftover of really what's going to happen. So 4xy is essentially the GCF. So 4xy, you distribute that out. That's going to give me 2x because 4xy times 2. You can kind of see it like this for the leftover terms. 8x squared y divided by 4xy, and we also have here 12xy squared, divide that by 4xy. That's kind of really what we're seeing here in this case, and yeah, that's kind of really what we're seeing here, if that makes sense. Alright, so now let's do this equation here as well. You guys can pause the video as well if you guys want to solve this one as well. Alright, so now let's do the same thing. The same thing, we're doing the GCF of 4, 8, and 2. That's going to be 2. And for the variables, if you do the math here, we do x times x from all these x to the 4 to the y, x cubed and y, and x squared. You can see here that we're going to get here, once you can see here that the commonality is that there's an x squared in all these. So you can do 2x squares, distribute that out, and then do all the leftovers, you're going to get that. So yeah. Now, how do we factor higher degree polynomials? This is the similar one here. How we would do this essentially for the first one. Let's just give you the first one, and then you guys can probably solve the next one. So first off, for factoring higher degree polynomials, you can just distribute first. So you can just first factor the individual parts. The individual parts first. You can just do that. So in this case here, we're seeing here that the first expression we can distribute that out because we're seeing here that the leading term, the 3 is the GCF for that, so 3, and we also have the x as well, so the x is also there, it's being distributed out, times 2x plus 3, and we're seeing here the same thing over here. This is a quadratic. You can do x minus 2, x plus 2, because, negative 2 minus 2x, that's negative 4x, and, the negative 2 times negative 2 is positive 4, so yeah, this is also, x times x is x squared. And we can see here afterwards, you can kind of write it as this, because the x minus 2 is being repeated. Now let's do the same thing for this one over here. This is a bit similar, but in this case, for this one specifically, so for this one, how we can distribute this first, we can first do x, so we can first just, same thing, so we can do this one here and this one here. Really, for this one, you can just distribute the x squared out. You can get x minus 4 in that part, and over here you can do the same thing, 6 times x minus 4. Always take a look at the individual expressions first and see if you can factor from there. That's kind of how you would do it for factoring higher degree polynomials in general. So you can see here that this is kind of what we're going to get there. So notice that we have the x minus 4 being repeated. That means that we can start writing, since this is kind of like, think of it like this is kind of like a like term for both of these. So it's being repeated multiple times. So you can just basically do x times 4, parentheses, x squared plus times x minus 4 times that by parentheses x squared plus 6. That's kind of really what we're seeing here. This is kind of like a like term kind of scenario here, because the x minus 4 is being repeated in this case. It's not like this one though. Let me be very clear on this part, because really what we're seeing here is that the difference between this and this, right? There's a clear difference. This is when they're being multiplied together. This is when they're multiplied together, you're gonna get essentially a square of that expression. when you're doing it individually, but they're kind of like separated into their own little expression individual parts, those can be considered as like terms. So those like terms, kind of think about it like this is kind of like terms in this part of the equation, and this is kind of really what's being factored out. This is essentially what's being factored and multiplied with these numbers. So you can see here, if you factor this out together and factor this out together, it's going to give you that, if that makes sense. So yeah, factor by grouping. This is kind of like factor by grouping. So kind of like, whenever I see it like this, it's kind of like, a like term situation. If you're seeing like terms in certain areas, you can factor those out by grouping afterwards. Let's do another one. Factor 2x to the 4th plus 4x cubed minus 30x squared. So we can see here, this is the same thing. Factor the GCF of the GCF of this term, and we're seeing here that the 2 is the GCF of the coefficient, and between all the x degrees, x squared is the common one for all of these. And then afterwards, you can start by getting the leftovers, and then afterwards, notice that afterwards you have a quadratic afterwards. You can do like a lot of things with the quadratic, but you can just do negative b plus or minus square root of b squared minus. You can do however many ways you want to do it with the quadratic equation. It's up to you. But you can also do easier ways, like just seeing here that we have a negative 15 and positive, so you can just do x plus 5. X minus 3. That's kind of how I do it. I always try to like visualize it first before anything for these equations. So yeah,